Okay, kids, we're back and we're talking about light again. And yesterday we went through once again this issue that was with physicists in the early days of talking about light. Was it a wave? Was it a particle? And then we found through experimentation that there's this, wave-particle duality that it has particles of both waves and particles. Now, one of the most important experiments that really turned the tide away from Newton was Young's double slit interference pattern. And if we were in class, we would do this. Now, I have put in a video for you to look at. It's someone actually doing what we would do. So if we would have been in class, we would have had a piece of glass that was painted black and two little slits in it. And on this side here, we would have had a light source. We would have used a laser. A laser. Okay. And the laser would have hit the piece of glass with the two slits in it. And here it's painted black. Here it's painted black. Here it's painted black. So no light gets through. But at the two slits, light gets through. And the light we would then shine onto a screen, and we would notice that right out here we would see an interference pattern where it would be bright, dark, bright, dark. So yellow is bright, black is dark. And the black is where we would have an area of destructive interference, a minima, right? And the yellow is bright, it's called a maxima, and its area of constructive interference on this screen. Well, kids, this is just 2-point source interference, which was known to exist for different types of waves like sound waves and water waves. So what they were actually seeing is this was very similar to any 2-point source wave interference. So this really, when Young showed that, hey, I can do this with light, things really started to change, and light was seen very much as a wave that Huygens was right and Newton's was wrong. Eventually, as you now have started to notice through the videos I've asked you to watch, that light has properties of both waves and particles, wave-particle duality. Now, the thing I want to remind you about 2-point source interference is there's a certain distance that a wave has to travel from this source to, let's say, right here where there's a bright maxima, constructive interference, and there's a certain distance that a wave has to travel from this source to this spot right here where you would have constructive interference, maxima bright. And there's a difference in that path. And that was what we were talking about the other day, path length difference. At the heart of interference patterns, I don't care what they are, I don't care what waves it in. At the heart of it is the fact that you have two sources of waves and they travel different distances to get to a particular point where they interfere with each other. Now, if they get to a point where it's bright all the time, I have it in yellow here, maxima, that means that the path length difference between the two waves, right? One wave traveled a farther distance than the other, is always a multiple of a full wavelength, which ensures that a crest from one wave always meets a crest from the other wave, and the same thing for troughs. Now, if you were to take a look at path length difference here for a minima, dark, destructive interference, there's still a path length difference from one source to the other source, right? This wave here had to travel a longer distance to get to this area of destructive interference than the wave from here, right? Well, at any place that you have a minima, dark, destructive interference, that path length difference, it always falls upon a multiple of half a wavelength. It always ensures that a crest from one meets a trough from the other wave. A crest from one source meets a trough from the other source. That's still at the heart of this. This isn't some type of uh, totally new experience we're having here. Young simply observed it in light. So let's take a closer look at this. Here are two slits. I'm going to call this slit source 1, this slit source 2, and the distance between them center to center is D. They are a certain length L from a screen, but we're using light waves that have very short wavelengths. So for all intents and purposes, this is L here, but this distance here is also L. All right. The difference is so minute compared to the size of the waves we're dealing with, their wavelengths, that all these distances from here, where the source is, where the two slits are, to where the screen is, it's L. All right. Doesn't matter that this hypotenuse is slightly longer, it's still basically L. And when you've got light waves hitting right smack dab in the middle here, we know that since it's the right bisector, the path that the wave took to get from there to there, from source 2, and the path that it took to get from source 1 there, there is no path length difference. It's 0, so you're going to get brightness there, maxima. Then you run into a situation up here where the path length difference between the two of them is half a wavelength, so you're going to get a minima there. Then you run into a bright area, and hopefully you will watch the video I associated with today's lesson, showing what we would have done in the lab setting. Right here, the path length difference is a full wavelength. Well, this is the first minima. This is the first maxima. So this pattern, as you saw in the video, continues on and on and on and on and on. Where are these positions in terms of an angle theta? So right here, let's say there's a point Pn, which is a point on any minima. It could be the first minima, the second minima, the third minima. Where is it? Where can I find this on the screen and describe it in terms of an angle? Well, kids, we already have the formula for this. We did it with the 2-point source wave interference pattern. We can use it for this one. If you want to find the angle at which a minima is, right, you use this equation right here. We saw that already. It's always on the multiple of a half a wavelength. If you put a 1, 2, 3, or 4, or 5 in here, you're always going to get a half and then multiply it. Similarly, if you want to find the position of a maxima, you get rid of the n minus half and you put in n lambda over d. And you can describe in terms of an angle, where a bright area would be. It's just this equation instead for a maxima, n1, n2, n3, and so on. Where would they be? Now, if you don't want to describe the position of a maxima or a minima in terms of an angular measurement, let's say you want to describe the position of a maxima, bright area, or a minima, dark area, in terms of how far it is from this right bisector between the two slits. How far is it from here to point Pn, a point on any minima, a point on any maxima? Well, you can do that because you know that the relationship here, theta, right? You got theta, well, opposite, right? Over hypotenuse, xn over L is your sine theta. So instead of having sine theta is equal to n lambda over d for a maxima, you replace it with xn over L because that's sine. Similarly here, for a minima, instead of using sine, you use xn over L. So those equations that we developed a couple of days ago now bail us out right here. They are bailing us out right here because we can use them to find the position of any maxima or any minima for Young's interference pattern in light. Now look, kids, I'm going to be honest with you. You know that huge derivation I went through the other day? It's good for you. It's good for your brain. You're going to experience more of these if you plan on studying the maths, the sciences, the engineering, the technologies. But for us, all we want is, here's the equation for maxima, angular. Here's the equation for maxima, linear distance from the right bisector. Here's the equation for minima, angular. Here's the equation for minima, distance from the right bisector. You're never going to have to derive these things or be able to, explain your way through how I get from a picture to these equations. You just got to know how to use them. So it basically is reduced to plug and play. What are the numbers? Okay, plug in the numbers, you get the answer. What are the numbers? Okay, plug in the number, you get the answer. All right, but I'm warning you, as you mature mathematically, you're going to have to deal with this at some point. Not now, but at some point you're going to have to. All right, you know me, I don't pull any punches. All right. Now here's another neat example I usually like to give you kids every year. Try to explain this one to you. You got a source here and a source here, like always. Young's double slit interference pattern. And they're a distance d apart. All right. And from here, they're all the way down here, and it's a large distance compared to the wavelength of light. The wavelength of the light has a very short wavelength. All right. It's a huge distance to where the screen is. How far? L. And at a certain distance, xn, there is a point Pn, which is a point on any minima. Then over here, see, over here, the green distance, not the blue distance. The blue distance tells you how far you have to go from the right bisector to get to point Pn on any minima. The green distance here, how far do you have to go from the right bisector to get to the next minima? Not the Pnth minima, but the Pnth plus 1 minima. Right? Where would that be? And there's a distance between the two of them, right? Here's the distance, delta x. Delta x, all right? That's the difference between the green length and the blue length. Well, what do we know? We know from our work that I have an equation that'll tell me where I can find xn. It's this equation right here. And I also can use that equation for where the nth plus 1 minima would be. Instead of putting an n in here, I put an n plus 1. Look, see? Look what I've done here. N, okay, nth one. N, okay, the nth minima. Okay, I get it. Nth plus 1 minima. Nth plus 1 minima. I just put n plus 1 in. And then I want to calculate delta x. How far apart are they? Well, it would be the green distance minus the blue distance, xn plus 1 minus xn. All right. Oop, what did I just do there? I have no idea. So then I plug in the equation for this one. Look, I plug it in. Minus, make that a minus sign. Don't know why that's not a minus sign. There we go. And I put in the equation here for this one. Now, what do we do next? Well, this is what our next situation is going to be. N plus 1 minus a half. Well, 1 minus a half is a half. So the n plus 1 minus a half just turns into n plus a half. Now I'm going to factor. So I factor out the lambda L over D. And what am I left with? I'm left with an n plus a half minus n minus a half. Well, n minus n is gone. A half minus a negative half gives me 1. So now I know that there is a constant difference in the x position. That delta x, which is, remember what delta x is? It's the position of the nth plus 1 minima minus the position of the nth minima, right? It's always constant. That's why we get that nice pattern you saw in the video that's equally distanced all the way through. And we have an equation for it right there. Okay? So kids, like I said, a little bit of plug and play. I just want you to be able to use the equations. I'm not going to ask you to derive anything. Okay? But this was a monumental thing that Young did. It threw the physics world for a loop because it really pulled people away from the particle model to the wave model, which eventually, as we saw from our video, led us to the whole concept of wave-particle duality, which changed the entire world of physics. All right, have a great day. Bye-bye.